Welcome to your lesson on energy, friction, and efficiency. This is your third topic in your unit on mechanical systems. So let's get into it. What we're going to learn today is a little bit about what energy is, how energy is lost by work done by friction, and then how we can calculate the efficiency of machines or energy conversions using a % efficiency formula. So, what is energy? Well, energy is defined as the ability to do work. So when you think about what work is, well, you know that work is applying a force over a distance. And you learned the formula for work as force times distance. So you can think about energy as the ability to be able to apply a force over a distance. And that energy could be because something is moving, or it could be because of state or position. A lot of different factors can come into this. So let's take a look and learn more about it. So first of all, talking about energy, we're going to talk about two main types or categories of energy. We have kinetic energy, which is energy due to movement. Okay, so whenever anything is moving, it has kinetic energy. And then potential energy is energy that is stored for later use. So it could be energy due to an elastic being stretched, right? When the elastic is stretched, that energy is stored for later use, and we can just actually see that energy get released by letting go of the elastic band. Or if you have something really up high, then that's potential energy because gravity is pulling it down. So by letting go of that thing, all of a sudden it is moving and having kinetic energy. So it's just energy that's stored for later use. Anyways, kinetic energy, a few examples, and really it's just anything that's moving, but a moving hockey puck would be kinetic energy. A gear turning, because it's turning, and turning is movement, that's kinetic energy. Well, potential energy would be things like a book on a high shelf, which of course could fall, and it's being pulled down by gravity. Or an example of the chemicals in fireworks, right? There we have chemical potential energy that can get released once the firework is lit and blows up. Then it releases its energy. But until that happens, it is potential energy. It's stored energy that can be used later. This is a nice diagram, but it's so tiny that I know it's tough for you to see, but it's splitting up energy into those two types, kinetic and potential energy. Some good examples of kinetic energy are mechanical energy, which is energy to motion or movement, electrical energy, which is energy that, from the flow of electrical charges. We have thermal energy, which is like heat energy. Radiant energy, which is like electromagnetic radiation stuff. We have sound energy as well, which is a type of kinetic. And then under potential, we have chemical energy, nuclear energy, gravitational energy, and elastic energy. The ones we're going to talk about the most here is gravitational potential energy and kinetic mechanical energy. Sometimes we just, because we use these so much compared to the different types, we just call it potential and kinetic. But when we talk about kinetic, we're talking about moving things, and we talk about potential, we're talking about stored energy normally due to gravity. So here's a great diagram to kind of show what I mean by gravitational potential energy. When something is above the ground, it has stored energy called gravitational potential energy. So this person does work to get to the top of the hill. And once they're at the top of the hill, they have all of this stored energy that they can release simply by going down the hill. At this point right here, it's all potential energy. They're getting ready to go down the hill. And then as they go down the hill, the energy that was potential gets converted to kinetic. So that stored energy is getting essentially released. Another diagram, very similar. We have down here, of course, a lot of kinetic energy, right? So when the person first throws or hits the baseball up or whatever they did, at this point, it's all about the kinetic energy. We call that normally EK. K being for kinetic. Well, the potential energy, assuming that it's close to the ground, would be at a minimum. Then as it gets higher and higher and higher and higher, we get to the top. And I don't know why I'm writing this because it literally just says it. But at the very top, for a brief moment in time, as it switches directions from going up to down, it is still. which means for that moment of time, we actually have very little kinetic energy, but we have a lot of potential energy because gravity is pulling it down and it's high up in the air. So hopefully those two examples give you an idea of what we're talking about when we talk about these kind of energies. EK, kinetic energy, is all about movement, while potential energy, in this context, when we're talking about gravitational potential energy, is all about how high something is, okay? How above the ground it is. So kind of an application of this. How is gravitational potential energy being stored here? And what form of energy will stored energy be converted to? So the whole idea here is that we have the water cycle, a lot of water evaporating from different things, like from vegetation, by transpiration, from streams, from oceans, from the soil, all sorts of places the water's coming from to make clouds. And of course, when we have the clouds, the water is all potential energy, gravitational potential energy, because it's up high in the clouds. And then as it falls down, that is being converted to kinetic energy, right? As it goes down, as the rain falls, that potential energy is changing into kinetic energy as it falls down. So what form of energy will stored energy be converted to? Kinetic. And how is gravitational potential energy being stored here? Well, because the water is above the ground in the clouds. All right, so let's talk about energy conversions. And energy conversions is when energy changes forms from one type of energy into another, which is something that happens all the time and specifically happens within like machines and devices. So a great example would be electrical to light energy when we have a battery connected to a light bulb, or gravitational to kinetic, right? Which is what we just actually dealt with the water cycle. Great, huge amount of examples there. Whenever you drop something, you're converting gravitational potential energy into kinetic energy. So that's an energy conversion because you're changing energy from one type to another. We can calculate the efficiency of any energy conversion or a machine that converts energy by using this simple formula. It might look complicated, but if you know anything about percents, this is just calculating the percent. All it is saying, well, how much energy did you get out of it? That's your output. How much energy did you put in? That's your input, times 100%. And then that gets you your efficiency. Think about this as like a test percentage. How many questions did you get right? That's your output. How many questions did you see? That's your input, times 100%. Now, efficiency cannot be over 100%. No machine can be 100% or more efficient, because that would mean that it's creating energy, that it's getting energy that was not there to begin with, and that is not possible. Energy cannot be created or destroyed. That is the first law of thermodynamics. So, as a result, our efficiencies will always be less than 100%. So here's a question. When we deal with this formula, output and input, which number is going to be the smallest, the output or the input? And the answer is the output. The output has to be smaller than the input in order for us to get a percentage less than 100%. So input is the energy or work going into the machine. Output is the energy or work going out of the machine. It makes sense, the keyword of in and out, right? It's pretty obvious. But sometimes students get confused and have a hard time figuring out what the input and the output is. So first of all, output will be the smaller one, the smaller energy value. But the other thing to remember is that input is the before and output is the after. Okay, so it's like the cause and effect. So when we think about a light bulb, the input energy is the electrical energy. Without that electricity, it's not lighting up. And then the output is the light. So yeah, hopefully that makes sense. We're going to do some practice on this to see how it goes. First of all, an official slide on what I said, that no machine is 100% efficient. So that is actually due to the second law of thermodynamics. That's the statement for the second law, is that things are always continuing to a state of more disorder, or the fact that no machine can be 100% efficient. In other words, there is always energy lost as heat. The first law of thermodynamics, which I talked about previously, and no, you do not have to know these laws. You learn them actually in grade 10. The first law is that energy cannot be created or destroyed, but just changed from one form to another. And then the second law is that whenever we change energy forms, whenever we change from one type to another, we lose energy in the form of heat, thermal energy. Anyways, we can't have a machine that's 100% efficient. It is not possible, or over 100% efficient. There is a whole branch of, I don't want to call it science, a whole branch of pseudoscience of people trying to get what's called an over unity machine. A machine that is over 100% efficient and has perpetual motion. Not possible. By the laws of thermodynamics, it is not something that can occur, but there are people who absolutely obsess over this, and they love magnets and hologram stickers and all sorts of kooky stuff. Not that magnets are kooky, but just anyways. And they devote their whole lives to this, some people, but it's not possible. Anyways, the output work of a machine is always less than the input work. This is the second law of thermodynamics. That's important for you guys to realize, that it will always be less. So when you're trying to figure out which number is which, the lower number between the two will be the output. And the energy is lost to thermal energy. It's not gone, it's just changed to heat. All right. What causes this loss of energy? So why is energy lost as heat? Well, the main thing is that there is friction. Friction is the rubbing of one surface against another surface, or one material against another material. We could even have it with air, right? Wings of airplanes go through air friction. When you deal with cars and stuff, they try to be more aerodynamic to lower air friction. But that has to do with, again, friction. So friction is the rubbing of two materials or mediums. Let's say mediums, that's a good term. Rubbing of two mediums together. And it's always going to be in the opposite direction, the force of friction, to the movement. So always against movement or motion. Oh, what am I doing? Oh, there we go. So how do we make a machine more efficient? Well, it's really simple. In order to make a machine more efficient, all we have to do is reduce the friction. So that's where things like lubricants, better bearings help. But by reducing friction, we can make machines more efficient. And we take a look at something like a car or an internal combustion engine. It's become incredibly more efficient as time has gone on, which is great, right? Unfortunately, what's happened is that as engines have become more efficient, then cars have become and engines have become more powerful, so that they don't actually use less fuel necessarily, but instead they get more power out of it. All right, so here's a diagram that talks about friction. So the box moves in one direction and the force of friction will go in the opposite direction. It will either oppose motion between two surfaces that's already happening, or that has not yet happened as you push on something and it does not move, but it's always in the opposite direction to movement between two surfaces or attempted movement. Last thing to talk about before we get into some examples of percent efficiency is energy transmission. Just so you realize this is different than conversion. In energy transmission, energy is transferred from one place to another without being converted or changed. So electrical energy, right? We end up transmitting electrical energy all over the place using power lines. What's interesting about power lines is it actually turns out that higher voltages are more efficient. than higher currents. So that's why we have high voltage lines, is so that less energy is lost by heat than if we had lower voltage lines carrying the same power or amount of electricity. So that's why we have the 100,000 volt lines, is because it ends up being more efficient over long distances. But that has to do with energy transmission, where the form of energy does not change, it's just moving from one place to another. All right, so let's deal with some percent efficiency calculations. We're going to use our full problem solving process here to get through this, and let's see how we do. Now, I like doing a little bit of a shorthand here, which I'll introduce with you as I go through. The input work you can do on a can opener is 24 joules. I'm actually just going to measure that or write that out as in. So I have in is 24 joules. The output work out is 18 joules. And the question is, what is the efficiency of the can opener? I normally write this out as a percent sign and then EFF, meaning efficiency. That's my question mark. So percent efficiency, as we learned, has the formula of output energy divided by input energy times 100%. So percent efficiency is equal to 18 joules divided by 24 joules times 100%. So I'm just plugging it in based on the values I have. So 18 divided by 24. We don't actually need a calculator for that, but we certainly could do one. This just basically simplifies to 3 over 4, right? 18 divided by 6 is 3, and 24 divided by 6 is 4. But let's go ahead and get a calculator. So in case you don't believe me, you can see it. And I have 18 divided by 24, and then times 100. And that gives me an answer of 75%. So my percent efficiency is equal to 75% for this question. And I'm done. Good, good, good. All right, let's move on. So let's try this one out. The work done by a lever is 5,675 joules. The work done by the effort force is 10,000 joules. What is the efficiency of the lever? This question is not being as explicit of what is input and output. So you tell me, what is the output here? And the output is going to be the smaller number. Remember that output is always smaller than input. So I have an output energy equal to 5,000, say one number and write another. 5,675 joules. My input energy is 10,000 joules. And I want to know the efficiency, percent EFF, is my question mark. So percent efficiency is equal to output over input times 100%. So percent efficiency is equal to 5,675 joules divided by 10,000 joules times 100. Another one where we actually don't need a calculator because I'm dividing by 10,000, so the answer will be 56.75, but let's prove it. 5,675 divided by 10,000 times 100. And I got 56.75 as an answer, so that's my percent efficiency here, just over half. So this would be weird for a lever, for it to be this inefficient. That means that like something is wrong with the fulcrum or the pivot. It's losing a lot of energy, but it is what it is for the question. So that means that in this scenario, I am losing 43% of the energy that is put in. It's being lost to heat, right? To thermal energy. So a lot of energy is being lost because it's very inefficient at turning input energy into output energy. This is a very different type of question, which is going to involve a lot of work. This would be Harder than what you'd see on a test, that's for sure, but I think it's interesting. It includes using two formulas, one that you already have learned before, and then today's. So calculate the efficiency of using the ramp to lift an object and then letting it drop from the top as shown. So I am first pushing it up the ramp, that's my input, and then I let it drop from the top of the ramp, and that's my output. So the way that we're going to calculate the energy for both is we're going to use the work formula. So we actually have like 3 big steps here. So let's start by trying to figure out the input energy. So I'm going to go ahead and say in here. My input energy, I have 200 newtons. That's a force. It's an ugly F. 200 newtons. And then I have a distance of 15 meters. So distance is 15 meters. I want to know my work is for the input. For the output, I've got a force of 400 newtons. And I have a distance equal to 6 meters. And I also want to know the work. So once I find the work for both of these, that tells me my input and my output energy. Work and energy are basically the same thing, right? Energy is the ability to do work. So once we calculate the work, we know how much energy it had. So let's go ahead and solve for this. So here, work is equal to force times distance. So work is equal to 200 newtons. I'm actually just going to move this over. I feel like I really squished things there. 200 newtons multiplied by 15 meters. And that means that at the end of the day, I have 3,000 joules. 200 times 15 gives me 3,000 joules. And then for my output, it's the same exact work. Work is equal to force times distance. I shouldn't say work in that context. It's the exact same process, I should say. 400 newtons multiplied by 6 meters, which means that I have 2,400 joules. Because 4 times 6 is 24, and I got 2 zeros. Well, let's prove it. 400 times 6 is 2,400. So now I can calculate the percent efficiency for this. So I have my input, which is 3,000 joules. I have my output, which is 2,400 joules. And I'm trying to find my percent efficiency. So that's my question mark. Percent efficiency is equal to out divided by in times 100%. So I have percent efficiency is equal to 2,400 joules divided by 3,000 joules times 100. And this is actually kind of, again, a funny one. This is going to equal to 4 out of 5. So 80%, but I'll show you. 2,400 divided by 3,000, 0.8 times 100 gives me 80%. So the efficiency of this system is 80%. So pushing the box up this ramp took 200 newtons of force over 15 meters. So it took essentially 3,000 joules of work to get it to the top of the ramp. And then once it was at the top of the ramp, it had 2,400 joules of potential energy, gravitational potential energy. So the ramp was 80% efficient, and 20% of the energy that was put in, the work, was converted to heat by friction. So why did we use the ramp at all? Well, because it took less force. By using a ramp, it was only 200 newtons of force that was needed to get it to the top of the ramp over 15 meters instead of 400 newtons. So using a ramp meant that we had a force advantage, right? We were able to do this with less force. All right, moving forward. In the previous example, how much energy was lost to friction? Well, we're just going to take a look at the previous example and the work we did. Our output was 2,400, our input was 3,000. So energy lost will just be equal to input minus output, right? Just the difference between. So lost energy is just going to be equal to my 3,000 joules minus 2,400 joules. It's just 600 joules. So at the end of the day, 600 joules of energy was lost to heat by friction as it moved up the ramp. And that's it. Hopefully that made sense. Have a good rest of your day.